Okay, welcome to problem 65 of chapter 10, and this is round 2. I just deleted round 1 because I made a silly mistake in the very beginning of the problem and then spent 15 minutes talking about it and got to the very end and was like, oh, well then. Alright, so we're going to start over. Or for you guys, it's actually the first time through it. We have this chimney. I'm going to call the height of the I'm going to call the chimney height H, capital H. And so we're going to use, as it suggests, energy considerations to figure out what's happening with it dynamically as it falls over. All right. And so here's the angle theta that's made with the vertical. And if you think about it, when we get to 35 degrees, which I'm just going to call theta for a while, because we got more general considerations later, so we're just going to express it more generically. When we get to 35 degrees, what has the potential energy dropped to? Right? Potential energy is dropped to mg h over 2, which is where the center of mass is, times the cosine of theta. Right? Because we start off, it's all potential energy. It starts falling. The potential energy drops, right? And we're treating it as, potential energy is just where the center of mass is. Potential energy drops as this falls over. Right? Eventually comes to a potential energy, eventually goes to zero. It's all kinetic at that point. So what do we start with? We start with potential energy equal to the mass of the thing times acceleration of gravity times the location of its center of mass, which is at half the height. All right. So this is the initial potential energy. Now, potential energy is a function of an angle theta we just went over with. That's mg times h over 2 times the cosine of theta, right? mg h over 2 times cosine of theta. So eventually the potential energy goes to zero. Well, potential energy is not the whole story, right? Because as it falls, it gains kinetic energy, and the kinetic energy is 1/2 I omega squared, right? Moment of inertia times omega squared. So if we put this all together, we got ui equals u theta plus k theta. K theta. All right. All right. So one of the pieces we don't have yet is the moment of inertia. But let's put it all together first. So we got mg h over 2 equals mg h over 2 cosine theta plus 1/2 I omega squared. Right? And the 2's disappear all over the place, and so we get, I'm going to put I omega squared on this side equals mgh onto 1 minus cosine theta. Okay. Or omega squared equals mgh over I onto this 1 minus cosine theta. All right. So now we know what omega squared is. We're after radial acceleration and tangential acceleration at the top. And the reason that I'm going after what is omega squared is that, the radial acceleration is omega squared r, right? And the tangential acceleration is alpha r. And we know from kinematics, omega squared minus omega naught squared equals 2 alpha theta minus theta naught. Right? And so we're going to get alpha from omega as well, since we're going to end up with alpha is 1/2 of omega minus omega squared divided by theta. Right? There we go. Okay, so that's alpha. It depends on omega squared and theta. So A tangential depends on omega squared, AR depends on omega squared. So here we have omega squared mgh over I, 1 minus cosine theta. We don't know m, and we don't know I yet. We know g, we know h. We know theta at the point that we're interested in. All right, so what is I? Generically, I is the integral of r squared squared dm. All right, so I'm going to write this I equals the integral from 0 to m of r squared dm. Now, if we think about it, we're integrating over this rod, right? It's spinning about a point at the bottom. If we take a little slice of it, dm, right? If we take a little slice of it, dm. What is dm? Well, that dm is, if we look at the total mass, m, times dr over the height, right? dr over the height is the fractional length of this piece, right? And so, or the fraction is the length of the fraction that this little dm represents. So m dr over h is dm, that little differential piece of mass, right? And so that means our integral I is from 0 to h. We've got substitution of variables in here. M over h r squared dr. All right. And this is because we have dm equals m over h dr. All right, the fraction of the rod, dr over h, times the total mass gives us a little differential mass. All right. Now, m over h comes out front, and integral of r squared is 1/3 r cubed, and we need to evaluate that from 0 to h. Right? I've not yet come up with a great way to do this. 0 to h. All right. And so the 0, of course, is 0. It's so 1/3 h cubed, which means 1/3 mh squared is the answer. All right, 1/3 mh squared. Now we could also do this using the parallel axis theorem. I is I center of mass plus mr r squared. All right. So if you look up in your book, the I center of mass for a rod spinning about its middle is 1/12 its mass times its length squared, right? And the parallel axis theorem, we got our mass. Now this is h over 2 squared, right? So we've got 1/12 plus 1/4 times mh squared. Now a 1/12 1/12, which is the same as 1/12 plus 3/12 mh squared, which is 4/12 mh squared, which is 1/3 mh squared. Okay, I have no idea why I switched to big M there. Little m, little m, little m, little m. All right. So we have the moment of inertia as 1/3 mh squared. We have that omega squared is mgh over I, 1 onto 1 minus cosine theta. So I now, we have our mh squared, right? And the 1/3, so the 3 goes out front, right? mh squared over 3. All right, so the m cancel out, you get a g over h. So omega squared is 3g over h onto 1 minus cosine theta. Now we're ready to answer part A. All right, now, just now, right? AR is omega squared r. It's omega squared r. R is h in this case, right? So this is omega squared h. All right, so that ends up being 3g onto 1 minus cosine theta. All right, so at 35 degrees, we're talking about 3 times g times 1 minus the cosine of radians of 35. Where did I mess up? Radian. Oh, I need one more. Oh, g. 9.8, right. So 5.32. 5.32 meters per second squared. Okay, part B. So part B is a little more complicated. We've got alpha. Okay, so in this case, and we want alpha r, tau A tangential equals alpha r equals h. Remember, r is h over 2. So let me just put r over 2 for now. R over 2, omega squared minus omega naught squared. Well, omega naught is 0, theta naught is 0, so this is going to be h over 2 omega squared divided by theta. All right, the only thing we need to make sure we do here is that theta is in radians. So h over 2, theta is in radians, 55. Omega squared we've got as, omega squared h, oh that's right. So omega squared has the 1 over h in it, so when we stick in omega squared we get 1/2 3g 1 minus the cosine theta divided by theta. All right. So 3g onto 1 minus cosine theta, the 1 over h and the h cancel out. And so now we stick in theta. So what is radians of 35 degrees? 0.611 or 0.6085. So 3/2 times 9.8 times 1 times 1 minus the cosine of the angle divided by the angle. 4.35 meters per second squared. That's part B. 4.35 meters per second squared. All right, part C. At what angle theta is tangential acceleration equal to g? All right, part C. We want AT equal to g. Well, AT is 3/2 g onto this stuff. All right, so we want AT equal to g, and the question is, when does that work out? And so we have 2/3 theta equals 1 minus the cosine theta. Two-thirds theta equals 1 minus the cosine theta. Okay. My apologies for going away for a minute there. Not that you guys really knew, but the video probably skipped a bit. Here's where we are. We have 1 equals 3/2 of this 1 minus cosine theta over theta. Right? And we're trying to solve for theta. And quite frankly, at the moment, I am stumped. I'm going to look for a little bit more and see if I can't figure out a good way to find this out. Okay, I have to admit that at this point that I am stumped because, one, I can't find an analytical solution. I can't not think of an analytical solution for this. Two, so I go over and I did this whole, let's do 3/2. 3/2 times that. So I look for it numerically, and it doesn't happen, right? Because the farthest we can go is 90 degrees. We only get to 95% of g. And so I don't, and let's double check at 35. That equals that times 9.8, so 4.35. Yep. So, I don't know what they did in the book to get the answer they got, but I get that there is no solution to this between 0 and 90 degrees. And we're just going to live with that right now until you guys can figure out what I did wrong, if anything. All right, on to the next one.